Here's my Lab 3 on gravity. Introduction. The purpose of this lab was to use computational means to calculate and model gravity and other forces acting upon a spacecraft to better understand how a changing FNet affects multiple objects at once. In this lab, we had no real experimentation, but rather two sets of code to model different scenarios that display physics principles such as gravitation, Newton's second law, net force, velocity, and position update formulas, and more. Overall, the results of the code were satisfactory, with the values of our mass as well as our velocity closely matching that of the TAs. Main physics ideas. While many physics principles were applied in this lab, I found that Newton's second, gravity, and the velocity update and position update formulas were most crucial, as they were the primary factors that drastically changed the output of the code when manipulated. We used the principle of gravitation, Newton's second, and the position and velocity update formulas to observe how multiple bodies in space interact with each other simultaneously. Before we get to our experiment, because we ran two separate experiments, each with their own system and surroundings and initial conditions, we have two sets. For our first model, our system was the star, the surrounding was the black hole, and the initial conditions were unknown. There wasn't much going on in there. For our second model, the system was the planet, the moon, and the spacecraft, and again, the surrounding was the black hole. Our initial conditions were the gravitational constant, the mass of the planet, the mass of the moon, and the mass of the ship. The experiment. In this experiment, we created two lines of code, both modeling different scenarios that hinged on the same physics principles. Our first model was of a star orbiting a black hole, and the second was a spacecraft, a planet, and a moon all interacting with our first model. The goal of the first was to find the mass of the black hole, and the second was to figure out what velocity our spacecraft needed in order to not crash into anything. Looking at the code again was relatively simple in both cases, with the starter code having most of the information ready to go. We did, however, need to input some lines regarding the position and velocity of our systems. The code also required some guess and check work in order to come up with a sufficient velocity for the second model, which was particularly fun in my opinion. Over here, I highlighted some of the code that had the most going on, and that's from the second model. So anything you see that's not commented out is something that we had to manipulate in order to get things working. Predictions versus reality. In this case, we found both of our experiments to precisely follow our initial predictions, as every force in our code was accurately displayed and no unaccounted forces were present to skew our results, as we have seen with the previous labs. While within the parameters of what we were trying to accomplish with this lab, there were no errors, if we were to somehow conduct our experiment in the real world, our results would most likely be very different, as many other factors would come into play that were not accounted for in our relatively simple code. Discussion. Overall, I found this lab to be quite interesting and quite fun, as the assignment was relatively easy while still highlighting how coding can be used in physics to greatly reduce the work required to perform accurate and tedious iteration. The guessing and checking of the velocity of our ship in the second set of code was particularly engaging, as it allowed us to see how small changes in the ratio between the x and y velocities can greatly affect an object's trajectory over time. What if? If we were to model everything with our system comprised of a black hole, a star, a planet, and a moon, we would need to include everything we had in our second model, i.e. the forces of gravity between each object, the masses of each object, the initial velocity and location of each object, as well as the gravitational force of the black hole and its mass as calculated from our first model. There would certainly be forces that proved to be more significant than others, as the force of gravity on the spacecraft due to the black hole would be far greater than the force of gravity on the moon due to the spacecraft. What does it mean? What is the difference between Fnet and rate of change of p or momentum? Fnet is the combination of all forces acting on both the parallel and perpendicular components, while the change in p or momentum is the change in overall velocity of an object, which is also comprised of perpendicular and parallel components. In both cases, the object can be observed as changing motion, but the key difference here is that Fnet drives a change in momentum, and the change in momentum is a direct result of an Fnet acting on the system. In conclusion, I found that this lab, more than any before it, has instilled in me an appreciation of computational analysis of physics. It highlighted how modeling multiple iterations using update formulas can greatly reduce the effort required in predictionary analysis, as well as gave a great visualization of how multiple bodies interact with each other with changing Fnet by using Newton's second. Thank you for watching, and please give me 100.